Today I want to talk about how we can transform exponential graphs, and in order to do that we first of all need to have a solid definition for what an exponential graph could be. So far during the course we are comfortable plotting functions and sketching functions which look like this, and we call these polynomials because it is some variable to the power of a constant. Now, what I'm going to introduce to you today is this idea of an exponential, and the reason it's called an exponential is because our variable is what we call our exponent. It's this power at the top, so therefore it is an exponential graph. So now we know what an exponential graph would be, let's actually look at y equals 2 to the x. Let's think about what this would look like in terms of a graph. Now, whenever I'm looking at something that I've not seen before, the easiest way to try and determine what it would look like is to just try some values. So I'm going to think about plotting in some values of x and finding their corresponding y value. So I'll just go from -1, 0 to 1 to 2. Okay, so let's think about this. We have a function of y equals 2 to the x. So therefore, as I increase my power by 1, I am going to be multiplying it by 2. My value is. So let's substitute in 0. 2 to the power of 0 is 1, 2 to the power of 1 is 2, and 2 to the power of 2 is 4. As we can see, as I go down, I'm doubling at each stage. So I'd like you to make a guess as to what you think 2 to the power of this -1 would be, and hopefully from our index laws, we should remember that that would be the same as a half. So now I have enough information, I think, to actually try and plot this graph. So I'm just going to draw a Cartesian plane. So I'm going to draw my y-axis and my x-axis. And I'm going to plot these points on and try and get a feel for what this graph would look like. So, having a look then. 0 and 1 would go through about here. Let me just put the x and the y, sorry. So 0 and 1 would be about here, and that's where it crosses through. A half would probably be about here. Let me just move this down a little bit. Give myself a bit of room. Okay, a half would be about there. Going up then, 2 would probably be about here. 4. And then the next one, well, we're doubling each time, so it would be 8 and so on. It would look really steep. If this is a half, then we'd have a quarter, then a 16th, and so on. So what's going to happen at either side? Well, if I keep on adding on a value, let's say as I go towards x equaling infinity, so as x approaches infinity, my y value, well, that's also going to approach infinity as well, because it's going to get infinitely high. Okay. What's interesting though is what happens when x approaches -infinity. So, as x approaches -infinity, I am halving my value each time. So it goes a half, it goes a quarter, it goes a 16th, an 8th, whatever. It just halves each time. Now, if I'm halving something, I'm never going to get below 0. So that means when I look at this graph, it is never going to go below that x-axis. So when I come to plot it, an exponential will typically look like this, and my x value, as x approaches infinity, my y value is going to approach 0. It won't touch it, it won't cross it, but it will approach it. What we do is we call this a certain thing. It is called an asymptote. And essentially that means that it is a horizontal, so this is a horizontal asymptote in this case, and it means that our line is never going to pass that point or go through it. Okay. So, how can we use this? How can we think about what happens if I want to transform my graph? So, the next one I'm going to look at is I'm going to look at the graph of just y equals 2x, y equals 2 to the x, and then I'm going to put +1. What's going to happen to my features? Well, if I think about it, my actual graph and all the gradient and everything is going to stay the same. All that's happening is I'm translating the graph up by 1. So therefore, when I come to draw my axes, what's going to happen is that my graph is just being translated vertically up by 1. So every key point is going to be changing vertically by 1. So my intersection point is no longer going to be at 0, 1. It would be at 0, 2. And then my horizontal asymptote is no longer going to be at y equals 0. It's going to be at y equals 1. And the way we denote that is typically with a dashed line. So to draw this, I'm just going to draw my line like this, and I'm just going to hope that we can see that it's dashed if I do this. And we would just draw our graph again. It would slowly get to 2, and then again it would go race off into infinity. And this would have a horizontal asymptote. I'm just going to call it horizontal asymptote at the line y equals 1 this time. So I'd like you to quickly just make a plot of the line y equals 3x to the power of x minus 4 and y equals 2 to the power of x take away 6 and y equals 4 to the power of x plus 3. I'd like you to make a plot of those in your book. I'd like you to work out what a horizontal asymptote for each one would be, and we'll have a look at that in the lesson. Okay, so moving on from here. The next thing we come to look at is, again, having a graph, but this time what happens if I change my power inside? So the way I would draw this is like y equals 2 to the power of x plus 1. Well, what is going to happen to this? And again, if it's tricky, what I'm going to do is I'm just going to plot some values. So I'm going to have my x and my y, and I'm going to substitute in -1, 0, 1, and 2. So at -1, -1 add 1 is going to be 0, so therefore my y is going to be 1. 0 add 1 is going to be 2, 4, 8. If we try and compare these values with the values we had previously here, well, if I carried on the next one, I would have an 8 in this situation here for 3. So everything that's happened is that my x value has gone back 1 space. So the corresponding y value and x value has just gone back 1 space. So when I come to plot this, let me just draw my axes. What happens is my x value, well, here, my intersection point is now at 1, is now at -1, about here. And my new intersection point is 2, because that is the value of x to the power of 0, or when x is 0. So again, when I plot this, it looks like this, and we just need to know that this is 2. My horizontal asymptote will stay the same because I'm not translating my graph vertically upwards. The only thing that has happened is that, let's say this is y equals 2 to the x plus 1. If I just draw on the same axis y equals 2 to the x, where this would go through at 1. So this is y equals 2 to the x. So when we have something in the power, let's say it's y equals a to the x plus b, whatever b is, it's just a horizontal shift of our graph. So our standard graph is the same. The last thing I want to talk about before the end of this session is going to be on different types of exponential graphs. So far, we've looked at y equals 2 to the x. It would make sense that if we looked at y equals 4 to the x, on the same axes, it would have the same intersection point and asymptote. However, it will be more sharp in terms of its gradient before and after the intersection point. So, what do I mean by this? So I'm just going to draw on y equals 2 to the x, and it goes through at 1. This is y equals 2 to the x. What I'm going to draw on now is y equals 4 to the x, and what we should see is that it is going to approach 0 a lot faster, and then when it cuts through the intersection point, it's going to approach infinity a lot faster. So this is y equals 4 to the x. What I want us to think about is what's going to happen with y equals a half to the x. So to approach this, first of all, I want to change this half to be something of like a 2 or a 4. I want it to be some sort of integer to the power of x. So to do this, I can use my index laws. I know that a half, well, if a 2 is along the denominator, that can be written as 2 to the negative 1. So therefore, I now have y equals 2 to the power of negative 1 and x, so it's to the power of negative x. So therefore, every time I substitute in an x value, it's going to give me the corresponding opposite to the one that I had earlier. So a value of 0 and 1 is going to stay the same for both graphs. Let me just change what pen I'm going to use. Let's use purple. So this value is going to stay the same because 0 won't change. However, if I substitute in the value of 1 to this graph, I'd get the value of negative 1. So it would be something like this. And then it would go again. So what happens is that the graph of y equals a half, well, y equals 2 to the negative x, is sort of like a reflection on this y-axis here. So that concludes today's session on looking at transformation of graphs. We'll be looking in the next lesson at how we can do stretches. But until then, if you have any questions, please let me know. Thank you very much.